Hello, everyone. So in this video, I want to work with these three equations, which are sort of the fundamental foundational equations that we have for working with problems in kinematics where acceleration is constant, and work them into a form that's a little more abstract, but sometimes a little more useful. So I'm going to do a little bit of math to get there. And what I'm hoping to get is displacement as a function of time. And so let's see how we can work with these equations to generate some new equations. So let me start by just pointing out what these equations are. So the first one is average velocity equation, just definition of average velocity as displacement over time. That's equation one, we'll call it. Equation two, this definition for average acceleration, equivalent to the definition for average velocity, just change in velocity versus time for average acceleration. And also this equation for the average velocity in the case that the acceleration is constant, where the average velocity is right in between the initial and final velocity. So those are our three equations. One thing I'll do here too is to say that if we're explicitly dealing with a constant acceleration case, then the average acceleration is just the same thing as the acceleration. So because the acceleration isn't changing at all. So I'm going to call the average acceleration, I'm just going to write that as A. And what that will mean is the constant acceleration for the time period that we're considering. Okay, so let me do a little bit of work here. So what I'm going to look for is some function for the displacement as a function of time. So let me take equation one, and I'm going to rewrite that as just moving the time over. So the displacement is the average velocity times the time. Okay, that's something. Now I'm going to try to work this into something where I don't have average velocity and I just have initial properties of the system. So what I'm going to do is I'm going to plug in equation 3 for average velocity. So that'll look something like this. Okay, and then I'm going to take my second equation and work with it a little bit. So I've got the acceleration, or I should write it like this. The change in velocity is equal to the acceleration times the change in time. If I work with that a little bit, I can say that the final velocity is equal to the initial velocity plus the acceleration times the time step. And then I can take this equation for VF and plug it in here. So if I do that, then I get delta x is equal to the initial velocity plus v final, which is initial velocity plus a delta t over 2 times delta t. And now this is a matter of just kind of expanding out. So I have one factor of vi and then another factor of vi. So that's 2vi, but over 2, that's just vi times delta t. So initial velocity times the time step. That's my first term. And then my second term is I've got a times delta t over 2 times delta t again. So that's 1/2 at squared. 1/2 a delta t squared. And this is the equation that I'm looking for. This is more abstract than any of the equations 1 through 3 that we started with, but sometimes it's more useful. What this says is if I know the initial velocity at some time, and I know the acceleration for the duration I'm considering, and I know how long I went for, I can figure out what the displacement is. And really all this is sort of a shortcut. For any given problem, given any particular numbers, I could go through this process of working with equation 1, plugging in equation 3, and then working with equation 2 to get something like this if I wanted to find displacement. But this is just a shortcut to kind of go straight there. This will always work as long as acceleration is constant. So this is, I guess I could write that down. So true if a is constant. So let me give you a few examples for how this can work. All right, so here's an example problem. There's a car driving at 20 meters per second, and then at some moment in time, it begins to accelerate at 0.5 meters per second squared, it should say. After accelerating, how far does the car travel in 1 minute? So we're going to assume that the acceleration remains constant for that 1 minute, and we want to know how far does it go once it starts accelerating in that 1 minute. So we can use this equation up here to do that, because in order to use that equation, we need to know what the initial velocity is, we need to know what the acceleration is, and we need to know how long we've gone for. And in this case, we know all these things. So this is kind of a plug and chug problem here, but to see how it works out, the displacement would be the initial velocity, 20, times the time, which should be in seconds. So 60 seconds is 1 minute, plus 1/2 times the acceleration, which is 0.5, times the time squared, which is 60 squared. If you work all this out, you get 2,100 meters. If you think about how you would solve this if you didn't use this equation, what you'd want to do is you'd take the initial velocity, you'd use the acceleration to find the final velocity, you'd take the average velocity and then multiply the average velocity by the time step. But if you do that, that approach is equivalent to this, just with more steps. So we've built those steps into this equation. So we just have one step. So we trade the intuition that we would have for how to do this problem with our first equations, which are maybe more intuitive and more natural, for the simplicity of using this. But you always got to keep in the back of your mind that we're just using a manipulated form of those basic fundamental equations. Okay, so another example. Okay, here's another example. If I drop a ball from rest, how long does it take to fall 3 meters? Well, let's try using our equation to figure this out. So I drew a little diagram over here. So I've got my ball here. I'm going to drop it from rest. If I'm dropping it from rest and I want to know how long it takes to fall, then I can take my time period to be from the time I drop it to the time it hits the ground. So that means that at the beginning of my time period, the initial velocity is 0. If I'm dropping it from rest, it started from 0 and it'll start to speed up. Another thing I'm going to do here is I'm going to define a coordinate system just to be careful. So I'll define down to be the positive x direction. So if I'm getting the displacement in the positive x direction, that will be equal to the initial velocity times the time, which is what I'm looking for, plus 1/2 times the acceleration times t squared. So how many of these things do we know? Well, we know what the displacement is going to be, actually. It's going to be 3 meters, because the time period we're considering is from when we started up here to when it falls down here. So the displacement in whatever time that is will be 3 meters. I'm going to leave that as a variable for right now. I'm going to call it h. We also know that the initial velocity is 0, as I just argued. So that'll be 0. This term will be 0. And then I've got 1/2 times the acceleration times the time squared. And I don't know what the time is. That's what I'm looking for. But I haven't been given what the acceleration is. And we have to think about that a little bit. So why is this ball accelerating? If I drop it, it accelerates because gravity pulls it down. And I haven't given you the acceleration due to gravity in this problem, kind of intentionally as a way to get you to think about the lab. But I'm going to call that acceleration g. So whatever that acceleration is, it's some constant value called g. And I'm just going to leave it in there like that. And the time it takes, we'll just leave that as delta t, because that's what we're trying to find. I can now solve this for the time, assuming that I know g. So the time would be, delta t would be, if I move the g over 2 over, delta t squared is equal to 2h over g. So delta t is equal to, I don't really have enough space over here, do I? So delta t is equal to square root 2h over g. So our height is 3 meters. If we know the value of g, we can just plug it in and get a number. Another thing you could do here is, let's say you don't know what the acceleration of gravity is. but you do have a stopwatch. So if you have a stopwatch, then delta t is just something you can measure directly. In some sense, this question, how long does it take to fall 3 meters, is a very straightforward experimental question. If I develop some technique where I can drop this ball with consistency and have it fall 3 meters, and I can reliably measure how long it takes to do that, then I can just measure delta t. And if I wanted to know what the acceleration due to gravity was, I can take my equation and kind of use it another way and solve for that value for g. If I do that, then I can say that g is 2h over delta t squared. And that's the value of the acceleration. What's interesting, maybe if you look at it, is that if you think about measuring the acceleration or calculating the acceleration based on a measured time, this is kind of convenient because it implies that all you need to measure is the height and the time in order to calculate the acceleration. You don't really have to know anything about the velocity as long as you start with a velocity of 0. And that makes measuring acceleration a lot easier than it might otherwise be. Because normally if you think about acceleration, you think about a change in velocity over a change in time, which seems to imply that you need to measure an initial and a final velocity. But all of that's kind of built into this equation because we used that equation for acceleration in this to calculate stuff or to manipulate it into that form. So that's kind of nice. So I'm gonna box that too because that's kind of a cool result. So you can measure the acceleration on this fall that way if you just measure the time directly. Okay, I think I'm going to leave it there. And I hope this was helpful as a way to think about problem solving. Okay, bye.